I would like to welcome you to the first video that covers the topic of chemical calculations. My name is Pavlína Marvanová and I will start with the basic chemical calculations. Chemical calculations are an essential part of the whole chemistry. The topic is extensive and we can't go through everything in detail in this course. But we will briefly mention the basic relations and solve some typical chemical problems to cover the majority of the topic. Let me point out one important thing. This topic can be managed by simply learning the theory or just knowing the right formulas. The best way how to manage it is by practice, solving. The more chemical problems you will have solved, the more skilled you will get. Therefore, as a part of this course, you will also get additional exercises for practicing. One of the most important properties that characterize all substances is the mass. For us, it is also important the mass of the particles of which substances are composed, the mass of atoms and molecules. We are used to expressing the mass in kilograms or in grams, but it would be numerically very low values in this case. It would be very impractical to use it for the calculations. Therefore, some variables have been introduced to make it easier. Let's go through them briefly. The first is an atomic mass unit, mu. It is defined as 1/12 of the mass of carbon nuclide C12. Numerically, the value of the atomic mass unit is 1.66 multiply 10 to minus 27 kilograms. Sometimes, the atomic mass unit is called the atomic mass constant because the value is still the same. And for us, it is one of the constants we have to learn by heart. Important is that the numerical value of the atomic mass constant is given in kilograms. When we want to use it, we have to use the mass also in kilograms. In chemistry, we do not always need to know the absolute values of the mass of individual particles. Therefore, the relative mass has been introduced, such as the atomic relative mass, AR, or the molecular relative mass, MR. Relative mass of an individual element is the ratio of its actual mass and atomic mass constant. These values, the relative ones, are characteristic for each element and can be found in the periodic table of elements. For example, the atomic relative mass of hydrogen is 1.008. Analogically, the molecular relative mass is the ratio of actual mass of the molecule and the atomic mass constant. If we take hydrogen as an example again, we know that under standard conditions it occurs in the form of two atomic molecules. Then the molecular relative mass of a diatomic hydrogen molecule is 2.016. In the calculations, the atomic or molecular relative masses are rarely unknown, because as we have already mentioned, we can get them from the periodic table of elements. But there is one type of calculation when we are supposed to calculate them and, commonly, then get the identity of the unknown atom or molecule. Let's try to solve the first problem. The mass of an unknown element is 1.79 multiply 10 to minus 25 kilograms. What kind of element is it? We can find out which element it is using the atomic relative mass, which we look up in the periodic table. We can calculate the atomic relative mass using the mass of the element and the atomic mass constant. The mass of the element is given in the task, and the value of the atomic mass constant we know. So, The answer for dividing 1.79 multiplied 10 to minus 25 by 1.66 multiplied 10 to minus 27 is 107.87. So the atomic relative mass of the unknown element we are looking for is 107.87. Looking to the periodic table of elements, we find out that the unknown element is silver. Let's move to another important quantity. The amount of substance allows us to express how much of a substance we have by the number of particles. The standard unit is 1 mole, and 1 mole is exactly 6.022 multiply 10 to 23 particles. This number is called the Avogadro constant, Na, and its definition is the amount of substance in 12 grams of the carbon-12 nuclide. The symbol for the amount of substance is small n. It is a very universal quantity, and it can be calculated in several different ways. We have already said that we can use the formula with the number of particles, the big N, which we divide by the Avogadro constant Na. Another way we can calculate the amount of a substance is by using the mass of the substance divided by its molar mass. The last method uses the volume of the substance and the molar volume. We will explain it in details in the following slides. Now let's look at the molar quantities. The first is molar mass. The symbol for molar mass is big M, and according to the definition, the molar mass is a mass of 1 mole of substance. The SI unit for molar mass is kilograms per mole. However, for historical reasons, molar masses are almost always expressed in grams per mole. Here we have the formula. Molar mass, big M, is a quotient of the mass, small m, and amount of substance, small n. Numerically, the molar mass corresponds to either the atomic relative mass of an individual atom or the molecular relative mass of the given compound. The molar mass is usually not the unknown in chemical calculations. It is either given in the task, or we can easily find or calculate it from the periodic table. For example, the molar mass of sulfuric acid would then be a sum of the atomic relative mass of hydrogen twice, plus atomic relative mass of sulfur, and 4 times the atomic relative mass of oxygen. The molar mass is 98.076 grams per mole. Another molar quantity is the molar volume. It is an equivalent for the molar mass, and its unit is cubic decimeter per mole. The formula for the calculation of molar volume is the volume divided by the amount of the substance. What is really important to mention here is that we use the quantity and this formula only in connection with gases, never for liquids, even though we know the volume of a liquid. It is a bit easier with molar volume than with molar mass. Molar volume is a constant. 1 mole of every gas under standard conditions has a volume of 22.41 cubic decimeters. Standard conditions refer to a specific temperature and a specific pressure, but we suppose that our calculation always proceeds under the standard conditions. So once again, molar volume, numerically 22.41, can be used only in calculation with gases, never liquids. Let's try to solve another problem. What amount of substance corresponds to 28 grams of iron? We know that the atomic relative mass of iron is 55.85. The unknown is the amount of substance. So let's look at what information we get from the task. It is the mass, and it is atomic relative mass. Both quantities, we know, are enough for us to calculate the amount of substance with this formula. After substituting the number to the formula, we can calculate that the amount of 28 grams of iron is 0.5 mole. Here we have another task. We have 10 grams of hydrogen. How many molecules does it contain, and what volume does it occupy under standard conditions? We know that the atomic relative mass of hydrogen is 1.008. In this case, we have two questions. The first is for the number of molecules. The second is for volume. Let's look how to calculate them. We know that we can calculate the number of molecules using the amount of the substance and the Avogadro constant. We know the value of the Avogadro constant. It is a constant, but we don't know the amount of the substance. It is also unknown for us. So let's look at the volume. We want to calculate the volume of a gas. And as it is stated specifically, the conditions are standard. This information can lead us to the molar volume. Thus, we can calculate the volume using the molar volume and again the amount of substance. We know the value of the molar volume. It is a constant again, but we don't know the amount of substance. In both calculations, we therefore concluded that we need to know the amount of the substance, otherwise we cannot move forward. Is there any way we can calculate the amount of substance except of these two formulas? When we look back at the task, we see we have there some information about the mass of hydrogen and the atomic relative mass of hydrogen. Thus, we can conclude that the amount of the substance can be calculated using these two quantities. What can be tricky? Don't forget that hydrogen as a gas commonly occurs under standard conditions in the form of two atomic molecules. So we have to count with the molar mass that equals to the atomic relative mass multiplied by 2. The calculated amount of the substance from 10 grams of hydrogen is then 4.96 moles. And now, let's return to the previous formulas. If we substitute the calculated amount of the substance into the calculation for the number of molecules, we find out that 10 grams of hydrogen contain 2.99 multiplied 10 to 24 molecules. And if, on the other hand, we substitute it into the formula for the volume, we find out that 10 grams of hydrogen under standard conditions occupy a volume of 111.17 cubic decimeters. To sum up, in this video, we had a short look at some basic chemical properties and quantities. We got acquainted with the atomic mass constant and the Avogadro constant and the relative masses of atoms and molecules. We have explained, and this is important, what is it and how we calculate the amount of substance. And we have also introduced the molar quantities, molar mass and molar volume. Thank you for your attention and see you in the next part. Dear students,